The path not taken, you're going to understand what that's about in a little bit. But before we start doing that, let's start talking a little bit about what thin slicing is. So thin slicing is sort of the heart and soul of BTC. It is the creation of a sequence of tasks that gets progressively more difficult, right? And it's built on three theories. So theory number one is flow. Mahai Csikszentmihalyi and myself. Theory number two is variation theory by Ferenc Martin. And theory number three is redundancy, which is based on Seller's work, Bruner's work, and so on and so forth, right? Bruner's work is why we have spiraling in the curriculum. Seller's work on cognitive load is very, very instrumental here. Let's dig into this, and I'm just going to take you through some of these theories kind of quickly here. So flow. So flow is this idea that flow is this state that we get into when we're so engaged in something that we don't want to disengage. And this was the sort of the brainchild of Mahai Csikszentmihalyi, and he found that one of the really important elements of flow, one of the things that was present was that whenever there was a flow state, there was a perfect balance between the ability of the doer and the challenge of the task. And he represented this in a graph. And he looked at this graph and he noticed that there were some zones, right? When there's high ability, low challenge, students are more likely to be bored. When there's a high challenge, low ability, students are more likely to be frustrated. And flow happens when we're in that perfect balance. And this was sort of where his work ended. He wrote a bunch of books, made $1 million, and went off in a different direction. But this is where my work on building thinking classrooms came in. Because if you want students to get into this flow band and to stay in this flow band, you're going to have to nuance the tasks, right? Because students do this thing, this annoying thing that we in the ed biz like to call learning. So if we can get them into this state and then their ability starts to increase, and now we have to increase the challenge. And then their ability increase, and then we have to increase the challenge. And this is how we maintain that flow state. However, this is more of a picture of thick slicing. Thin slicing actually occurs when we think about making very small adjustments to the task. And this is not actually quite how it works either. So for example, let's take a look at an example of a task on factoring quadratics. Now we picked this one, it's in the book. Factoring quadratics, if we want students to factor quadratics, this is a very nice place to start. And you see these tasks, and they get progressively harder. As the more factors are at play, it's getting harder and harder and harder. But they all have this commonality to them that they are all sort of type 1 tasks. Their leading coefficient is 1, everything is positive. And no amount of doing these is going to prepare the students for what's next, which is all of a sudden we introduce some negatives. And then we eventually introduce leading coefficients. And when we do that, the tasks actually change fundamentally. So a more accurate drawing of the thin slicing is one like, oh yeah, sorry, I forgot about this one. It's one like this, which is where, yeah, go ahead, where there's a bunch of tasks that kind of fall into one type, and they all have very incremental change. But then there's a fundamental shift in the nature of the task. We introduce that negative, it changes things. It's a big jump in complexity, and now we're kind of staying there in type 2. And then there's another big shift when we introduce that leading coefficient. And this is sort of an updated, sort of true to form description of what thin slicing looks like. So that's one aspect of thin slicing. The next one is variation theory. So for variation theories, the whole purpose of thin slicing is that we want students to figure something out. We want them to discover for themselves some patterns. We want them to recognize things. We want them to figure things out. And in order to do that, they're going to have to notice things. Well, Ferenc Martin recognized that the only time, like what we notice is we notice change against a backdrop of things being the same, right? So we want to see variance, we need to see invariance. So take a look at this image, right? So let's pretend we're standing in this meadow and there's no wind. Everything is absolutely still. It's pretty, but our eye is not drawn to anything in particular. Likewise, let's say we're standing in this meadow and there's a breeze. So everything is moving. The grass is moving, the flowers are moving, the branches on the trees are moving, all the leaves are moving. Again, it's pretty, but our eyes aren't drawn to anything. But then let's take a look at this idea that we're standing in the meadow. There is no wind. Everything is perfectly still, but one branch on one tree is rustling. Our eye will be drawn to that. And this is the whole principle behind Franz Martin's theory of variation. We notice things that are changing against a backdrop of things that are not. And so part of creating this thin slicing sequence is we need to have variance and we need to have invariance. And then the last theory is the theory of redundancy, which is that just because the students have learned something doesn't mean they've learned everything before we need to increase the challenge. And especially if we have them working in groups, we need to have them have more and more experiences with one type of task before the challenge increases. So all three of these together kind of creates this theory of thin slicing. So now let's take a look at an example. So how do we thin slice? So for this, I'm just going to quickly say we use our existing resources, right? And then we have this idea, like, let's pretend we're using a textbook. Our textbook has all the tasks in it, but they're not in the right order. So what we do, and I do this both figuratively and literally, is we're going to flip through the book. Let's say the book, we're going to look through, we're going to identify the range of tasks that we want to engage with. And then we're going to give it a bit of a shake because that loosens up the tasks. And then we're going to toss them in the air. And now they're all floating up there. And now we're going to sort. And when we do the sorting, what we're going to do is we're going to pluck out a task and we're going to like, oh yeah, this is a type one and this one's a type two and this one's a type three, another type one. Ooh, this one's a nasty piece of business. And I'm talking to you high school teachers, we're going to save that one for tomorrow because as high school teachers, what we want to do is like, ooh, this will get them. Right. And that's not what we want to do because we're trying to get them to notice patterns and so on and so forth. So we're going to take you through an example.
Yeah, so we're going to look at the concept of just adding fractions. And we recognize that, some of you might teach adding fractions before grade six, even though we mark it as a grade six. Where we are in Canada, we actually teach this in seventh grade. But regardless, it's a comfortable example for us to illustrate how this all kind of comes together. So the first thing we need to recognize is that kids have seen things before when we're adding fractions. Like we need to recognize that they know what a fraction is, they know what it looks like pictorially. Maybe it's as part of a set instead of a whole. They know how to represent them on number lines, which we then maybe we might be connecting to how they're adding fractions. Um, Maybe they've seen pictorially or concretely how to add a fraction by just using manipulatives or drawing them out. And most importantly, maybe not most importantly, but very importantly, they need to understand equivalent fractions, right? And usually a good way to do that that's happened in previous grade levels is this, using a visual model. Now, what's important here is I don't need them to have mastered these perfectly, right? We just need them to have seen them before because when they get into the groups, this idea of knowledge mobility will allow them to catch each other up. I don't need to do a full-on review of every one of these things right to get started. But let's dive into this. So let's imagine we went through our book, like Peter said, we picked all these ones that are floating in the air. These are the questions we found that might be floating in the air. If we're going to be teaching adding fractions as our next topic for our next task, these are the 12 different ones that we've come up with that are different than each other. Take a minute, we'll set a timer here, we'll mute ourselves. Take a minute, look at these fractions. How might you do what Peter said and sort these? How would you group different ones together? How would you sort them? Take a moment, look at your screen.
Yeah.
Um,
And you want to sort them into three types, type
Three
one,
types,
type two,
yes.
type three,
Thanks, Peter.
and then within a type, sort them as well. So just take a moment. We'll give you 1 minute.
Start my timer. Okay, it's been a minute. Um, I'm sure you realized as you're doing this, there might be a few different ways to sort our fractions or fraction addition statements here. Some of the ways you may have done this, one of the ways you may have done this to start is by looking at the types of denominators, right? If I look at this image here, and many of you probably went this, I think I saw it fly up on the chat. The latest shade in our screen here, we sorted by common denominators. Our medium-ish shade we'll go with is, not common, but not totally uncommon, right? These are what we call friendly denominators. They're multiples of one another. They
Yeah.
play
And in
nice.
some places in the world, they call them related denominators.
Oh, I like that. I like that. Okay. And lastly, our darkest shade. These are the less friendly, the unfriendly, the uncommon denominators. Maybe you sorted it this way.
You paid attention to it at least. Or
Mhm.
maybe you paid attention to the type of fractions. You were sort of considering, I'm going to work with proper fractions first and then mixed fractions second.
Right. Or maybe you were looking at the actual where this question is going to take you. Let's look at the sum of the fraction, right? If we're looking just the fraction portions, especially in the mixed number ones, is the sum going to be greater than one or less than one? And maybe we can sort them into two categories that way.
And of course, you had to kind of pay attention to all of these as you were sorting and so on. But you would have maybe come up with something that looks like this.
Right. And so in this section, in this, arrangement, if you will, if we look at type one, two, and three, we've definitely sorted them by the common denominator, right? Common, friendly, uncommon. But within the type, we've also sorted it from top to bottom. Our first one is the one that's going to be less than one. Our second one's the one that's going to be greater than one within the type of having not mixed numbers. And then the second two, what we're looking at here, we've got the mixed numbers, but the first one, the fraction portion, is going to be less than one. The second one, the fraction portion, is going to be greater than one. So we've kind of got this three-way progression happening within
Yeah.
this sort.
So your primary here is denominator, your secondary is type of fraction, your third one is the sum of the fraction part. Or you may have sorted it like this, which is the primary is the denominators again, but the secondary, this time we're paying attention to the sum of the fraction part. We want the sum of the fraction part to be less than one before we move on to the sum of the fraction part being greater than one. And then within the sum of the fraction part, you're putting the proper fractions before the mixed fractions. So there isn't just one possible sort here. So which one is perfect? So I do about 120 lessons a year in K to 12 classrooms. I spent all last week doing working in classrooms. Um, or not all last week, but a part of last week. Um, I do about 100 thin slice lessons a year. How many times do you think I've come out of a lesson and gone, that sort was perfect? Laminate that baby. We don't have to change anything. Um, that has happened 0 times. At the same time, how many times do you think the students have been sitting around the dinner table that night going, Mr. L really blew the sequence of tasks today, right? Like that's also 0. So how do we know? No one got it perfect. We never get it perfect. I never get it perfect, right? Um, Getting perfect is not the point here. Right. It's not, what I can tell you is it doesn't matter how you sorted it, it's better than whatever resource you got the tasks out of because the resource was designed on a principle of the students are going to learn or you're going to teach them and then they're going to practice. Here, they're actually learning through engaging in the sequence. So getting it perfect is not the point, right? The difference between a good sort and a bad sort is really comes down to how much just in time support you're going to have to provide. If the sort is really good, then you can watch what's happening more. If the sort needs improvement, then you're going to have to engage more with the students in real time to compensate for the fact that some of these jumps were a little bigger than we expected.
Yeah, and that's the reality. But that sequence that we just looked at, the 12 different fraction questions, isn't necessarily enough. So what was missing? Right? What do we need to think about to round this out to be something that we can do in the entirety of whatever length our class period is? And this is where that idea of redundancy comes in, right? We take what we've had, we plunk it into a bit of a table maybe, or maybe you've got lists, but then we need to reinforce these concepts through more questions of the similar type and subtype, if I could say that. We need to make sure that we've got enough of these questions built in here so students aren't just seeing that one type of question once and never seeing it again. We want to give them that opportunity, should they need it, to hit this a few different times.
And as we're working with the students, it's better off going into the lesson with more tasks than we need because it's easier to take them out than to try to come up with one on the fly. So this, what we've just taken you through so far, is what Kyle and I did when we wrote this book, right? Like we started with the shaking and tossing, we're sorting, then we're introducing the redundancy, and then we're trying it with kids. We're trying it, and we're making revisions. Sometimes those revisions are on the fly. Sometimes they're revisions that we make after the fact, but we're making revisions. And what you got to experience through that process that we just went through is what we went through. But so let us share with you now some of the sorts that we came out with. And one of the things we have to understand here is like the fraction one. What you saw is those two particular sorts. The first one you saw was the one that I tried first when I was working with students. But then we learned that that we could improve on that. And what you saw the second time was what we learned from that. So as we went through this process, we were sorting, we were testing, we were revising. And the ones we're going to share with you today are sort of the paths not taken in the sense that the the path that we first pursued turned out not to be the path that we ended up putting in the book because the path we first pursued is the more logical, more reasoned, more obvious path. And it turned out not to be the one that was best for students. You want to say some more about that, Kyle?
Yeah, no, really, like there's a lot of options here, right? We have, and we're gonna show you some of the paths that we didn't take, and hopefully give you some insight into how we thought about this as we planned, as we worked through this, and maybe inspire you to try some of these paths not taken as your starting path or one of the paths that you pursue when you're starting to plan for whatever topics you have. Because despite this book having 30 curricular tasks that follow the structure we talk about, we don't have all things for all people, right? Think of all the content that has to be taught from 6 to 12 math, like you're getting a tiny piece of it, but we hope that this can model some of the ways you can do that. So maybe let's jump into our first path, Peter. That
Yeah,
sound
let's go for it.
so the first path not taken is the because we've always done it this way path. Um, and we've picked two examples out of the book to share with you. And the first one comes from the topic of completing the square. Now,
So the way we've almost always done, and this was actually our first attempt, was we've thought of completing the square as, okay, we're going to have a bunch where the leading coefficient is 1, um, and the middle coefficient is even. Like this is really important, right? Then we're going to have the leading coefficient 1 and the middle coefficient odd. And then finally, we're going to add a leading coefficient that's not 1. And this is sort of the standard approach to having students engage in tasks that are completing the square. And indeed, after we had done our sorting and then like our shaking and tossing and sorting, this is kind of what we came up with as well. We had thin slice sequences inside of each of these, and then we tried it with the students. And what did we learn?
and when we tried it with the students, we realized it actually worked better to go this route. The students would rather deal with having that coefficient and factoring that out rather than dealing with the fractions that emerge when our B coefficient isn't odd, which kind of surprised us, but it made a lot of sense once we kind of got into the sequence. And if you work through the sequence, you're going to see it flows in a really interesting way. And let's talk a little bit about how this sequence ended up in our thin slice. We called them tax sequences within the book. So
Yeah.
our type one, we're just looking at our simple graphing in general form. Just convert one form to the other form. And you can see we've cherry picked just a few. We could show you all 10 different ones of each type, but the screen would get cluttered. You wouldn't be able to read it.
So these are really like when we have it in graphing form, it's great, right? It's easy to draw this parabola. But what if I gave it to you in the general form? How would you draw the parabola? And this sort of creates the impetus for making that transformation from general to graphing form. So those were the type ones, as we showed. Then the type twos, again, we started with it already being in graphing form so that they have this experience of, of converting from graphing form to general form, so that when it becomes time to convert from general form to graphing form, they're actually going backwards on a path that they've already traveled.
Yeah. And while they're thin slicing, there might be this little bit of that reverse engineering that's happening, right? And we do have some callbacks within the sequence. So they're seeing the same one in opposite forms and seeing as they progress through the task. And then ultimately we end with our our type three, with the B being an odd value, right? So to make those work when we're expanding out from graphing form, we have to have the fractions in there. But they're able to unpack this through the sequence.
Yeah. So the next one we played with was that we're going to share with you comes from trig ratios. So trig ratios has almost always universally been taught from the perspective of we're going to do sine and cosine. They come together almost exactly. And then we do tangent, which is sort of the ugly cousin of sine and cosine that we try not to invite to the party, and we try to leave them out as much as possible. It's because sine and cosine has that nice association. We try to leave tangent off to the side, right? But what we found actually was that it was way easier to start this unit with tangent.
Yeah.
Yeah.
Why would we start with tangent? Now, in the last one, we realized that the students actually preferred using tackling the factoring before the fractions. In this case, we realized conceptually, maybe tan was a really interesting place to start because we could make this really interesting connection to something they've already seen before, and that is slope. Now, this only, math speak, it only works when we're working in quadrant run the way that we want. But if we can make this connection from tangent to slope, we're really building and rooting this experience in something that they're already well versed in at this point in their math journey.
And this lesson is written from that perspective. In the launch sequence, it's all about, hey, we're going to show you a button on your calculator that connects the angle in a triangle to the slope of the line. And so it has this really concrete connection. And not just that, but a way for them to connect with it so that they can make sense of their answer, right? Because if the slope is greater than 1, the angle is greater than 45. If the slope is less than 45, the slope is going to be less than 1. So they have this really strong connection to sort of make sense of, we have an angle, can we figure out what the slope should be, and so on and so forth. So the sequence we enter in through looks like this. The type ones,
Sorry, just clicking through.
yeah, is we're giving them an angle and we're asking for the slope. That's how it starts. And they do a couple of those, but by the time they get to question 8, we're now asking them to find the rise given the angle and the run.
Type 2, we switch into now instead of finding the rise, we're going to find the run. So hopefully, build that quick little transition that they're changing their ratio and what's the unknown and solving that way. Flows really smoothly between types 1 and 2, but you might have to do a little bit of intervention to make sure that they're isolating the right thing as they're setting up their equations. And to be very clear, you're going to, unless you have that standard pack of calculators in your classroom, you're going to be spending some time making sure that they're not in radians, making sure that they know how to use the tan button. Like you're going to have to spend a little bit of time there, but well worth the investment during that type 1 while the task is much more accessible for our students because they're going to need it as they move forward. Then we're into type 3.
And type 3 is a little bit interesting because now we're going to have them find the angle. And a lot of people are really stumped in how the students would actually figure this out. But often by the time we get to trig ratios, students have learned how to find an inverse operation using a calculator. And if they haven't, they'll say things like, we have to untan it. And you just really have to share how to do that with one group, and then that knowledge will spread like wildfire. But what's really interesting about this one is that, yeah, we're finding what the angle is in question 16 very simply from the ratio. But when we get to question 23, this gets a little bit more subtle because how are we going to find the angle when we're not given the run? They're going to have to run Pythagoras to get that third side so that they can then use inverse tangent. But this also sets up sort of the segue into the next lesson in the book, which is like, hey, if you don't like Pythagoras, we got another button for you. Right. So it's sort of like creating that impetus where we're coming off a tangent as a really strong cognitive connection between slope and angle to this other ratio that we can use to bypass having to use Pythagoras.
Yeah, this task is a lot of fun. You'd be surprised. But again, back to this idea of like going against what we typically do. Starting with 10, you'll see there's this really good conceptual understanding that's built right from there. And then in the book, we don't talk about it today, but guess what task 48 is all about? We get into the other ratios, right?
Yeah.
Building on this understanding of how tan works. Now we can get into sine. Now we can get into cosine. Um, let's go into another path that we did not take.
All right. So this one is packed for every season. So sometimes when we're teaching, we have this feeling like we have to give the students everything up front, right? Like we got to tell them everything that they need to know, just in case you're going to hit rainy weather, you better bring something. Just in case you're going to hit cold weather, just in case you're going to hit sunny weather, just in case, packed for every season. When we're teaching, we tend to want to pile all that just in case up in front. This is Julie Dixon's terminology, right? We want to, and so we have two tasks we're going to share with you around this one. The first one is weighted average. So
Yes.
just in case.
Just in case, you might want to give them this wonderful formula that explains how weighted average works, and you can even use some notation, and we can go through this and we can tell the kids exactly how everything is going to work, and we can give them some big sets of data where they're going to have repeating values and they're going to have to do sort of weighted average. Maybe we're starting with how you handle what happens if you only know the percentage of a certain amount of data is a particular value,
Yeah.
or
We can just create a sequence of tasks that actually leads them to it. So we started with from the perspective of just average. The students all come into this lesson knowing what an average is. We review it in the launch, but let's do some averages. It's not there's just some number sets that we're finding the averages of.
right. And if you look closely from your teacher, your lens of teacher, you'll notice something happening through those questions, the three examples that we've pulled out of there, right? The first few were started with just a typical average, a few numbers, but look where we end in question 10. And then we move into, if that's question 10, look what we did with question 11.
Right. So what if we have a lot of numbers, like ridiculously large sets of numbers, so that we don't want to write it out as addition. Now we're going to have to write this out as multiplication. And the students naturally start to shift towards that sort of multiplicative thinking in their averaging. And we have some word problems
Yeah,
associated.
we sneak some word problems in at the end, usually near the end of a type within a task sequence. Well, we might sneak in some word problems because we recognize that that's part of when we flip it out of the book, you've got word problems that are floating in the air. Where do they fit? We're going to talk a little bit more about word problems later, but they can fit within this as well. Type 3.
Now we're starting to shift from the type twos, and if you pay close attention, 21 looks like a type two, and so does 23. But what do you notice about we're starting to get up into these numbers where it's starting to get close to percentages, and now we can shift into percentages.
Right. And I don't think I included in the screenshot, but I think we do have one in the sequence where the total number of numbers, if you will, is 200, right? So it's
Yeah.
not we're jumping into this 152 value and they're having to figure like it's a logical progression against, building on that variation theory that Peter led us through earlier. And if you
Yeah.
take them all together and you look at the sequence start to finish, it's impressive how far kids can get in a short amount of time without us having to pack for every season, without us showing every little thing they might need to know before they start this lesson.
And like all the other lessons we've shared so far, each one of these we've taken students through the entire sequence in one lesson, which means we're covering tremendous amounts of content within one lesson. We're pruning as we go, right? Like you're provided with 10 questions, and I may not need all of them. And I may need some for some groups, but not others. So, we're getting through all of the concepts within one lesson. So the other one we wanted to share with you was area formulas for quadrilaterals, triangles, and so on and so forth.
Yeah, moving into this idea of compound areas of compound shapes. And you might be tempted to use something like this. This is just, a formula sheet that I pulled offline. But usually, if I think of, oh, I'm going to have all these compound shapes that I need my students to be able to solve their areas for, let's give them all those areas ahead of time. Here's how you do a rectangle. Here's how you do parallelograms. Here's what triangles are, trapezoid. Like we go through the sequence of here's all the formulas you might need to use. Maybe we even lead them through an example or two on how to use it, just so it's top of mind for everybody. Again, we've kind of went against the grain here in thinking, maybe we don't need to give it to them explicitly for all of them. Maybe we can start simply and they will, in some cases rediscover the formulas, whether or not they've internalized them the first time they've seen them, but maybe this will spark their previous knowledge. So if we
And
start with a type,
I've used this lesson to actually bring students to figuring out the formula of a parallelogram and all different types of triangles on their own.
yeah, right, beautiful. So here's where we start.
We start there. Like look how far back we're starting, right? We have this metaphor of let's back up the train as far as necessary to get all our students onto the train. Look at that first question. What is the area of this rectangle? Right? Like we are going way back and we're building our way up. Just simple stuff. We're just finding the areas of rectangles.
Just finding the areas of rectangles and working our way back. And then we actually, when we transition into type two, we're kind of doing the same thing, right? If I look at those first two questions that I've got listed, which are actually different sections of the task sequence within type two, we're still just got the boxes, right? The squares where a student could count them out to verify their answers. But really what we're hoping the students to recognize with our strategic sequence and recognizing those subtypes is that these translations are useful to recognize within some of these areas, right? If I look at 18 and 19, the chunk that is sticking out on each side is actually the same size as the chunk that was cut out of the other sides. Like, is that something we can use to further develop our understanding of how we might find an area of a compound shape?
And that allows us this idea. There's actually three types of compound shapes here. There's the additive shape, which is where it's like it's one shape plus another shape. There's a subtractive shape where there's one shape taking away a shape. And then there's that sort of translational shape where the shape that, as Kyle mentioned, that is being added is also being subtracted. And we need that when we get into the type threes because that's going to help the students actually figure out how to calculate the area of a parallelogram. And then a triangle just ends up being a diagonal, like part of a parallelogram. And we're missing some of those questions in here, but you can actually see how a triangle is half of a rectangle. Well, an acute triangle is half of a parallelogram, and it's the short diagonal, whereas an obtuse triangle is half of a parallelogram where we take the long diagonal. And the students actually figure this out on their own through this sequence.
And some of this is just how we set up those early diagrams in the early types, like the little dash lines that we have to get them to see that those are little triangles that are connecting back to these translations. Makes a lot of sense. Because I want to address this, I saw this pop up in the chat. There's no way we're keeping up with the chat, but how do we give these types of questions to kids? We use this. Is that okay if we take a second to talk about that, Peter? Right. We use we have vertical banners. You might be familiar with that through more symbolic tasks, but we also have what we call a horizontal banner, where maybe we have these cut up in little pieces of paper where we can give groups the next one when they're ready, or maybe they come and grab it. I also find a community banner works well. Peter, is that something you want to speak to?
Yeah, so a community banner is if we're going vertical, like if we go back to completing the square, I'm just writing up a task and then the students are stealing from it. We have one board that's a teacher's board where we're just writing up the next task. When we write the fourth one, we erase the first one, we erase the fifth one, we erase the second one. We try to keep only three tasks visible at a time so they're not overwhelmed. And they're not overwhelmed by the work they have to do, but also not overwhelmed by the work they have done. For this type of task, we may have a community banner that's on a table where I'm putting out the first stack and students come to get it. And then when they need the second one comes out, and then the third one. And then when we add the fourth one, we take away the first one so that they're just perpetually working. They don't know how much they've done. They don't know how much there's left to do.
Powerful way to keep the kids going until the very end of a task, or until we need to consolidate and close it up. All right, we want to talk about another path we didn't take. And
So
we call this and now for something completely different path.
which is something that we see in textbooks all the time. We get asked so often about what do we do with word problems, right? So let's talk about some word problems, right? So here's a resource with some word problems. So what are we noticing here, right?
right? If you start to read these, and we'll speed this up a little bit for the sake of time, but first question, we're talking about scales between a house and a model house. Second question, for some reason, we're talking about elephants and cars together. Third question, we're talking about a flagpole and a woman and their shadows. And the last one, the last of the fourth, we're talking about distances on a map and the scales between actual distances of two different cities.
And the cognitive load on the students having to decode all of these word tasks, word problems is tremendous, which means that the more cognitive load that's being put on the decoding of the words, the less cognitive load they have left for doing the math. So we have taken a different path.
Right. And we're going to show you two different versions of this. The first one is the same topic you just saw on the last slides of word problems. It's all about scale factors and how do we, scale between two different representations of something. And in this case, we chose some new plans for a community center's, yard and area outside. There's a pool, there's a patio, there's a fire pit, there's all this free space. But we also need to talk about the engineering, diagram, so to speak. And again, these aren't real engineering diagrams. That's not where we're going with this outcome, or this learning objective, but we start pretty simple.
Yeah. So we have the diagram on the right is the actual space, and the one on, or I mean, on the left is the actual space, and the one on the right is sort of the scale drawing. And then we start asking questions around the relationship between these, the scaling that's happening.
Right. So those first ones are a lot of these, like, what's the scale? And then we move into, like, they're just the side lengths, the linear measurements, as we accurately labeled it. And then we move into type two, where we're doing the same thing, comparing the two different representations, but we're looking at areas and how area scales within scale factors. And
And then the
sorry,
third one.
do you want to speak to this one? I like this one, Peter, a lot, where you went with this one here.
So the free space one, and I actually did this lesson, I remember in Algebra 1 class. The free space one was really interesting because creating that space for the students to decide what they're going to do with it was really motivating for them. And so now we're still doing linear and area measurement, but we're now giving them some ambiguity that they get to play with, right? So we're creating parameters, and now they can decide what kind of a facility they want to put there.
Mhm. I think that sometimes gets lost in this idea of thin slicing. Like, there's this path we have them going down, but now within this, we've opened up some space for the kids to be creative and apply some of their knowledge in a really interesting way. And like we compared to before, like, the context has stayed static throughout. Nothing has changed. We might have the students even draw up, a big scale version of this, and they're slowly adding in different values as they find them, right? It works which is exactly how we'd want them to do it in a normal question, but because the context stays the same, we're able to go so much deeper with it.
Yeah.
Let's look at, oh, sorry.
Yeah, let's go to the next one, linear
Okay.
relations. And I just did this lesson this week, actually, with a group of seventh graders. So the teacher I was co-teaching with had been working on linear relations and these sort of abstract ideas about the relationships between, like, when is something linear and when is it not linear, and what is a connection between scale and so on and so forth, but it kind of in pieces. And then I come in and say, let's just do this task. So one of the challenges when we have linear relation word problems is, again, we got problems coming from every possible direction. We have one context, and that context is that we own a hot dog cart. And we own this cart, and we just have a bunch of tasks related to this hot dog cart that we're selling. And what we want the students to do is we want them to make a table of values, and we want them to draw a graph. And the type one tasks are just these linear relations, right? And it's just about, I made $2 a hot dog, I made $3.50 per hot dog, and it's just linear starting out of the origin, right? But then the type two, all of a
Yeah.
sudden now,
All of a sudden, we have to factor in that maybe we don't just get to sell for free. Maybe we got to rent the space. Maybe we've got to pay a fee to be at, the farmer's market or the night market. And if you notice this, like, the format, like the word problem structure, if you will, once they've decoded it once, they can really rip through these really quickly and understand the concepts that we're working through
yeah.
within that same context, like we've been talking about. We get into type three.
Type threes, we now have startup. money plus profit, which is sort of like I'm being asked to come and they're paying us to set up the cart. And in some of these, we're actually having to sell at a loss, but we're being paid a huge amount of money up front. Others, we're paying a huge amount of money, but we don't charge for the hot dogs and so on and so forth. So there's all of these sort of variances which allow us to actually explore all the possible linear relations that we can create out of this, and yet the context stays the same. And like I said, we did this with seventh graders this week, and by the end of the lesson, I was able to just set a scenario, and the kids were able to tell us exactly what the graph was going to look like without a table of values. And then we were able to talk about, well, what if I charge more per hot dog? It would be steeper. What if the fee to get in was greater? It would start lower. And they were able to just connect all this. And we covered so much ground. And all of the abstract ideas of linear relations really became concrete through this engagement with this task.
Yeah, the mental load becomes on the math, not the decoding of the text on every single one of these. A beautiful example of how we don't have to change the context for every little slice of our sequence. Let's go on another path we did not take. I like the title of this one. This is
Here are
our
pink socks.
fear of pink socks. Where does that come from? Maybe we don't want to mix our laundry together. Keep the whites separate from the darks, and definitely don't make sure there's no red in there with the whites because, I mean, dyes have changed, but I've had some pairs of pink socks definitely emerge before. So the parallel we're trying to talk about here is, we're often tempted to teach topics in isolation, in their own silo, keep them completely separate from one another, because we want to make sure that kids aren't getting confused between topics. We kind of, in an example of this that we're going to illustrate comes from our idea of lowest common multiples and greatest common factors.
So we may do a whole day on LCM and then a whole other day on GCF, or we may even spend multiple days on LCM and then shift over to greatest common factor. And it's that siloing that happens. And I think everybody who's ever taught this has had this experience where you ask students, I'm going to give you two numbers. I want you to find the LCM and the GCF. And the students put the same answer for both because they can't remember which one is which. And this way they're sure that they got something right. And that's part of the consequence of keeping things separate.
Yeah.
But what if we take the risk of getting some pink socks?
Let's risk it. It's in fashion now. And in this task sequence, we started with type one. We're not even worried about the greatest common or least. Like we're just worried about like let's review multiples and factors because we got to back that train up like we talked about earlier. And we use some special notation to make our lives easier here, right? M of two, if you will, is what are the multiples of two? Like that's where we're starting. And every kid in our, let's say sixth grade class, seventh, wherever you're teaching this, can start there.
Yeah.
And
And
there's
then what
another
are the
piece.
factors of 12,
Yeah.
right? Like let's start with that. And let's just start with multiples meaning M meaning multiples and F meaning factors. And then we go to the type twos. We're still not interested in LCM and GCF. Now we just want to find multiples that are common and factors that are common, right? And so we're introducing this idea that C means common, and we're just building up to it.
And then, ta-da, type three. Now we're into like, okay, you've got the common factors. Which one is the least? You got the common multiples. Which one's the least? You got the common factors. Which one's the greatest? Slowly leading us into this concept from the ground up of lowest common multiple and greatest common factor. Another thing I wanted to point out here, Peter, if you're okay with that, is we did include some word problems like we talked about earlier. Except, I mean, it's kind of hard to see, but we should have layered these differently. What do you notice about the word problems? Right? The first one's always about Alicia and her basketball, and the second one's always about Marcus and his, trying to share amongst friends, which is a really interesting way. So that idea of keeping the context the same, we're kind of doing that at a smaller scale when we're trying to implement the word problems within this sequence.
Yeah. And what's really nice about this one is if you've ever asked students to define for you what LCM is, they have a difficulty doing it. But what we're doing here is we're not starting with that definition of LCM. We're just building it up intuitively, right? And we have some questions at the tail end here about some interesting things in the consolidation, but we're not talking about that today.
No.
All right.
Another path not taken. Yours is not
Yours
to
is not
reason
the reason
why.
why.
Just
So
invert
this
and
is this.
multiply. Well, there, yeah.
Yeah, yeah. And of course, this is yours is not the reason why I just invert and multiply, which is
Yeah.
about fractions, but we're not doing that one. We're talking about sectors of a circle here. And we're so tempted often to start off with a formula for the area of a sector and so on and so forth. And we don't do that. In this task, we don't start with a formula. The formula is what emerges out, and not even in the formal sense of a formula, but as a process. What we start with is the area of a circle. And the story on this is um, I live on a farm, and on this farm, there's a goat. And this goat eats everything. So the farmer has had to tether this goat to a stake, and they use a 10-meter tether. And and this goat, they just move this tether around, and the goat's out in the field eating their circle of grass. Every few days, they move the goat until the farmer gets a cow. And now the cow and the goat are kind of in conflict. So the farmer had to move the goat. He had to take him out of the field because the cow needs the field. So now he's tethering the goat to the barn.
Absolutely. And this is how we build our thin slice sequence, right? We start with a variety of buildings, right? So look at how we've tethered the first one right in the middle. And our hope is that the students will quickly recognize, and they always do, that, oh, that's just half of that circle. Because we're using the same length rope throughout, it really keeps a consistent through line and really focuses on
It's
that
always
very,
10 meters.
always 10 meters.
Yeah. And the
And then,
second one we're getting that is the first one where they see a portion of a circle, but they
yeah.
can see that it's going to be a quarter.
hmm And eventually we do get into like 30, was it 37 degrees of a
Yeah.
like they're gonna get there within that first chunk.
Yeah.
This the
And
type two is sorry, Peter, I love this task. We it gets really interesting. And you know, top left here, our first one, like yeah, or we call it Loki in the book, but the goat can't get all around to the one side, but his rope is 10 meters long. That side length is only 8. What happens then? And we slowly progress through a sequence of barns where he's going to be able to kind of swing around the corner of buildings. And ultimately, we land in situations like this, where there's even more different sectors and smaller circles being formed as he catches different corners of the building.
yeah. And there's a fence adjacent to the building that he can wrap around if he gets to the end of it. We also did the same idea with arithmetic series. We don't start with a formula. We actually just start with a sequence of numbers and a series of numbers and show them how to add numbers from 1 to 100 and then take them through type 1 questions. We're starting at 1 and we're going to some number n. Yeah, we need to see the type 1s. And then the type 2s, we're starting at something other than 1, but still going up by 1. And then the type 3s, we're now skip counting. And the formula just emerges from this sequence.
The thing I love about this sequence is as they're working through the type ones, we say, okay, now come up with a formula, right? Come up with something that could predict this. They come up with something that works for numbers that start at 1, and then you throw one that doesn't start at 1, and that breaks their formula. And they're consistently revisiting and developing their own formula that I actually like a lot more than the formula we would have gave them anyways.
Yeah.
It's another great task that we've got included in here.
And here comes one of my favorite task sequences that we came up with, two to prove, which is about two-column proofs, right? So many places that I visit and I'm in schools are still doing two-column proofs, despite the fact that in many places the standards actually don't call for two-column proofs. It calls for reasoning, that they want the students to be able to reason. So if we're adhering to that, two-column proofs is just one example of that. We actually created 2 lesson sequences around this, and we're approaching proving as solving. So in the first sequence, all we're doing is we're giving them a diagram and we're asking them to solve for the missing parts. And they actually work on the diagram and they can just fill in things as they go. They can put a 90 there, they can solve that, they can and they're just adding to the diagram as they go and eventually work their way through to get to the missing side or angle that we've asked them for. So we're approaching this from a perspective of reasoning as solving. All right, not justifying, just reasoning as solving. That's the first lesson. In the second lesson, we start off with the same idea. You're now going to solve. But Kyle, you want to speak to this
Yeah,
one?
but as you're solving, we want you updating your diagram and showing us how you know. This is that reason. This is the justification that's coming through. So in this case, I know that A has to be 35 degrees because the sum of the angles in a triangle has to be 180 degrees. And we continue through this progression. And this is what we model with the students and are encouraging them to do with every single thing that we show in this task, right? And we slowly progress through, and eventually we end up with these diagrams that are just marked up with all these justifications all over the whiteboard space that they have. And our thin slice sequence looks very similar to the last one that we had. And in fact, a lot of the diagrams are very similar. We've just changed a few values here and there, but the expectation of what we're asking the students to do has changed because it's no longer just the value.
Right. So in the first lesson, all they have to do is add values to this as they're solving. But in the second one, every time they add anything to the diagram, whether it's an angle or a length, or they're introducing a new line, they have to write a justification for what it's doing. But we're not doing it in that sort of linear textual format of a two-column proof. It's now living in that two-dimensional space of the diagram. And there's some great tasks in this sequence.
Yeah, we've had a lot of fun
Yeah.
playing with these as we made them as well. Like it was quite the experience. But we want to be very like as we kind of watch the clock and near the end of our time together, we want to talk about this word, perfection, and we want to be
I mentioned
very
this earlier, right? Like the
yeah.
goal is not to be perfect.
Goal
We're
is
not
not
claiming any of these sequences are perfect. What we're claiming is that they're better than the original sequence that we pursued, like the path not taken, right? The original sequence was that path that was the obvious one. And then we realized that there was a better sequence through our interaction with the students in the classroom. And that's what this talk has really been about is what are the paths that the students have revealed to us are actually better paths to follow? Again, not perfect. Every one of these task sequences, you might have to add parallel tasks. You may have to take away tasks, right? And then when you use it with your particular demographic, as you're going through the type ones, you may realize that, oh no, my group of students, because of what they've seen before, this is actually turns out to be better. And then you can make these modifications as you go or after the fact.
That's what this is all about, right? Like I look back at some of these tasks. I was doing a task just on Friday with a group of teachers, and I realized I would change this now, right? Like these tasks that we've compiled in this book. Again, we're not claiming that they're perfect, but they are, the result of a multiple iterations. You need to take that risk and try something and reflect. And how is it going to be better the next time? Recognizing also that some of you teach that one topic once a year. So how are you going to keep track? Think of that as you get one shot at this year. What are you going to do next year when you come back to this? This is a problem you're going to have to solve and think through how you're going to capture that. But keeping some sort of notes might be a way to do that.
The second time you do it is way better than the first, but not nearly as good as the third.
Absolutely. We want to thank you for joining us on a Sunday. This is your time. Teachers don't have a lot of free time, and we are more than grateful that you spent some time with us today. On the slide here, we've got a cover of the book. If you want to see some of these tasks, we reference them throughout the session. We have social media presences where you can find us and follow along with what's happening in the Thinking Classroom world and Peter's work and my work and our team's work. We've got a few links on there specifically, and if anyone wants to reach out, I've listed my email on there. If you want to find Peter, I'm sure I can point you in the right direction.
Yeah. And I'm sure you could figure it out yourself.
Yeah.
If you want to get a copy of the PowerPoint, that bit.ly or the QR code will take you to a registration page where you register yourself, and then you'll get an email which takes you to that power. The PowerPoint's not there yet.
Yeah.
So this PowerPoint is really fresh,
Yeah.
but we will put it there.
That is great.
Awesome. Awesome, gentlemen. Thank you so much for taking the time on a Sunday. Who knows what day it is in Oslo over there? Just kidding. It's well into a Sunday for you there, Peter. And Kyle, I know you're just behind us here in Ontario. So nice early Sunday for you. But we appreciate it. And I want to, just share, as I hope others will share in the chat, big takeaways. And I think, that last piece about perfection, I think, is so important, and we have to always remind ourselves, right? And in a way, what came to mind for me was almost like, as educators, we're almost like thin slicing our own practice. And, you're going to do it a little by little, better and better each time. And it's not about making it perfect, just little bits at a time. So I thought that was huge. And I think we have to remind ourselves of that more explicitly. So thank you for doing that for us here today. Friends, this session is over, but we have many other sessions going on. And actually, I'll be jumping into another room to co-present with John Orr in just a few moments on designing large-scale PD. So if you are looking at doing something like that, feel free. We've got another session with James O'Neill Jr. going on right now. You can hop in there. As a reminder, this replay and all replays are going to be going up on the Summit platform. So you may have to do a refresh, make sure you're logged in, all of those wonderful things. However, they will be going up shortly after each session is complete. Remember, your free ticket, you have access all day up till about midnight Eastern time here. To be honest, we'll probably, keep it open until tomorrow, and we'll keep the Summit site open for an extra day. So don't stress about that. Enjoy, take the time, watch the sessions you can, and of course, you can always extend your access for $29. And in doing so, you'll unlock the opportunity for PD credit hours. I know some people require them for licensing or for their districts or otherwise. So hopefully that will be helpful for you. And remember, if those certificates are not populating right now, we will address that issue for you as the week goes on. So do not panic. We will not leave you hanging. We'll make sure to take care of you. Once again, we want to thank our sponsors. And in this session in particular, I think Whitebook is the sponsor that I want to highlight, given all of Peter's work around vertical non-permanent surfaces. So great tool, great company. Head on over to makemathmoments.com/Whitebook 2025. If you'll be leading any type of presentation or PD in the near future, they would like to assist you in that endeavor. All right, my friends, that is it for me. If there's anything we can do to help you, do reach out. But in the meantime, I don't want to hold you up from getting on to that next session. Enjoy. And thanks again to Peter and Kyle on a Sunday morning. We'll see you all soon.
Thanks, everyone. Take care.
Thanks, everyone. Bye.